Last time we were talking about chemical bonding, I left you with a question. And the question was, is there anything in between ionic and covalent? And you knew the answer, because why else would I ask it? Well, the answer is yes, polar covalent bonds. So what's a polar covalent bond? Well, the short version of the story is it's somewhere in between ionic, which is transfer of electrons, and covalent, which is sharing of electrons. So let's remind ourselves of the bonding types that we know so far. Ionic bonds and covalent bonds. Well, ionic are, this is how you recognize them, this is what happens, and again, the crystal lattice have included it because it is kind of important, but it's not really something that we're going to focus on. And then covalent bonds have different formation, different properties, and some just different stuff. Okay, middle ground. If you go back to a periodic table and think about particularly electronegativity, if you think about the trends, if you think about where things are going, so start with chlorine with chlorine. That was the example we used last time, and I just borrowed it from there and brought it here. It looks like this, and if we were to draw a real simplified picture of it, it would look like that. Chlorine has an electronegativity of whatever it is. The other chlorine has an electronegativity of exactly the same thing. So if I have that bond and I'm using the stick between them to represent the shared electron pair, if I had the bond between them, they are exactly the same. Now, hydrogen and chlorine are a little bit different because they will have a different electronegativity. And hydrogen, I know, is kind of a goofy one because it's off on the side, but hydrogen is going to have a lower electronegativity than chlorine. And we could guess that just from the trend in the table, but we would want the numbers, I suppose, to be extra sure, but hydrogen is a lower electronegativity. So when they bond, well, hydrogen is still a non-metal, so it's still going to be a covalent type of bond, but I do have the numbers. But the trend would work as well. The chlorine then pulls on that electron more strongly than hydrogen does. Remember, electronegativity is how strongly does an atom pull on electrons. So they're both pulling, a bit, but chlorine is pulling a little bit more. So the electron that's being shared, or electrons that are being shared, I guess, are pulled closer to the chlorine and a little bit away from the hydrogen. So we're not really going to do this picture here with the hydrogen dot chlorine and try and figure out a space. And even when we draw the more stick model of it with the line, we're still not really going to differentiate between the stick in this one versus the stick in the chlorine one. But it's something that we're going to have to think about and remember that what's going to happen is the electrons are being pulled closer to the chlorine. Now there's a couple of ways we can do this, but the little squiggle there, that's a Greek letter called delta. Now if you're thinking delta is a triangle, that's uppercase delta. This is lowercase delta. But what it means is there's a slight positive charge on the hydrogen side and a slight negative charge on the chlorine side. We don't want to talk about a charge because that's ionic, but a partial charge. So if a covalent bond is equally sharing, no difference between them, and an ionic bond is talking about full ionic charges, well, the middle ground must have some kind of partial little bit of charge going on with them. That's a symbol we use. Again, normally we're not going to write the delta positive, delta negative, squiggle positive if you want. We're not going to write those in, but every once in a while we need to be thinking about it. A couple of other ways to look at it, right? We've got this one here where the bubble of the balloon is trying to represent the electron density. So in one you've got nice even electron density, electron cloud if you will, around both. The bottom one is ionic, there's no overlap at all. And in the third one there, where the electron's kind of sucked away from one, pulled over to the other. Again, we're not really going to draw that, it's just different ways to represent it, different ways to think about it, so we can hopefully understand it. Okay, so I've got two atoms going together. I know how to tell if they're an ionic bond because it's a metal with a non-metal. What if it's two non-metals? Well, we have to be able to tell if it's going to be covalent or polar covalent. What's important for us, and this is where we want to focus, is we aren't going to have to be able to say, yes, this one's covalent, or yes, this one is polar covalent, but it's comparing two. This one is a little bit more polar, or this one might be a little bit less polar. That's going to be important for us. Generally speaking, we know this one, all right, if it's metal with a nonmetal. If it's nonmetal with a nonmetal, well, now we have to look a little bit closer. If the two atoms are close together in electronegativity, which for us generally means close together on the periodic table, they're going to be more likely non-polar. If they are a little bit farther away in electronegativity, a little bit farther away in the periodic table, then they're going to be more likely polar. Now, of course, the way the trend works, it might not work every single time, but we want to have a good handle on the periodic table. If we can use that periodic table as a tool for everything, then it's going to be we're going to be in good shape. Okay. Best case scenario, you have the periodic table with the electronegativity numbers. Test case scenario, you won't. So then you're looking at the trends. Okay. So, but the trends, if we go back to that, the trends are what we know: top to bottom, left to right, more or less. Now there are sort of rules about electronegativity differences, and when do you start calling it ionic, when do you start calling it polar, when do you start calling it nonpolar. Don't write these down. I know I left it too late. You're already in the middle of writing it down. If you have it, that's great. It's not going to hurt you at all. But the idea is that a low difference means they're fairly close together. They're sharing pretty well. Middle-ish difference, they're kind of far away from each other, so they're sharing but not equally. Big difference is they are transferring. But notice even the range for transferring, that's a pretty big range, 1.7 to 3.3. We can talk in class of how they get those numbers, and it doesn't really matter right now. What is kind of important is the fact that they are kind of arbitrary. You can have something that's a fairly low difference but still behaves fairly polar. You can have something that's in the 1.7 but still behaves polar rather than ionic and things like that. So it's a real smooth transition. That's not hard and fast rules. That's important too. Okay, that's really all there is to polar covalent bonds. From here, what we're going to do is try and get a handle on what does that mean for properties. Structure determines properties, and as we work through all this stuff, we're going to spend a lot of our time trying to figure out what it means for the properties. Taking properties and say, okay, how did that happen from the molecular structure? That's really all there is to it. We'll talk to you in class.